So let's just talk a little bit about Cryo-EM map improvement. And the things I'm going to talk about, some of them are generic and some of them are from this wonderful list of people who have contributed in particular to density modification. So Paul already showed a slide that looked a lot like this that kind of shows the many things that you can do in Cryo-EM with Phenix tools, from the starting map to map improvement, map symmetry. And we're going to focus now on the map improvement for a minute. And later we'll talk about model building and probably a little bit of docking. And you can, once again, ask questions all the way through. So we have 3 different tools in Phenix that allow map improvement. And one of them is automatic map sharpening. And map sharpening is not going to fundamentally change a map. It's going to change its appearance. Density modification is going to fundamentally change the map in that it's going to change not just the relative weighting of coefficients as a function of resolution, but it's actually going to change the content of the map. And then the third tool we may or may not get to, depends on how long this takes, is combining focus maps to create a combination map that's kind of good everywhere in the map, not just in the parts that are the focus map. So let's talk for a moment about automatic map sharpening. So here's a map that's, I'm adjusting the sharpening on this map, making it blurred, more sharpened, over sharpened. And once again, the only thing that's really happening here is we're changing the relative weighting on the Fourier transform of this map as a function of resolution. And I think kind of the best weighting of the Fourier coefficients leads to the map that you're looking at right now, which leads to a so-called B value of about 20. This B value is the same thing that's used in crystallography to describe the fall off with resolution of the relative weighting on Fourier coefficients. Now, how could we automatically obtain this weighting? How could we make this decision without us having to scroll back and forth and figure out which is the right one? Well, one way to do this is to notice that if the map is too sharp, then it has a lot of noise in it. And if the map is too blurry, it has no detail. So what we're going to try to do is we're going to maximize the detail in the map. And at the same time, we're going to try to maximize the connectivity of the map. So if the map is very detailed, the map has a high surface area. If you look at the contours in this map has a lot of surface area. When it was blurred, the surface area was much lower. If the map has a lot of noise in it, the connectivity is low. And so we're going to try to maximize those two things together. And we generated a little function that combines those two properties, the surface area and the connectivity, and call it the adjusted surface area. And we just maximize this quantity. And that, amazingly enough, leads to a pretty much optimally sharpened map in most cases. So now let's actually do this. So I'm going to stop that presentation. And now we're going to go to Phenix and we're going to actually sharpen a map. So everybody who's interested, I want you all to do that. And so I'm going to assume that you can start up Phenix somehow or other. So I have an icon here that I can use to just click on to open Phenix. If you have Phenix in your applications directory, open it there. If you open it from a command line, open it there. If you don't know how to open Phenix, type in the window and someone will answer your question about how to open it. if you open in the Phenix for the very first time, it'll ask you a couple questions. Just say, okay, okay, okay. And then you should get to a picture that looks pretty much like the one I've got here. And now I'm going to type into the chat window how to set up the tutorial data that we're going to use. So Phenix comes, so here we go. So Phenix comes with tutorial data and of many, many tutorials. And we're going to do one that's called major capsid protein of group A rotavirus and its auto sharpening. So here's how you find that tutorial. We go to new project, and I'm going to click on new project, and it opens a create project window. And there's a special part of at the bottom of this, it says set up tutorial data. So I'm going to click on that, and it's going to open a window that now says select a data set. So I'm going to push down on that, and then I'm going to scroll down. It's quite a ways down here to Cryo-EM. There we go. Cryo-EM, and I want one that says auto sharpen map. Right there. So if you select auto sharpen map, group A rotavirus, then it'll come back to the same tutorial setup window, and you can tell it where to put the data for this tutorial. You can put it in your documents, wherever. I'm going to browse and put it in a particular place that I set up for doing these, what I call it demo. Wherever you put it, just hit open, and then it will put the data in that place after you hit the button OK. So we're going to hit OK. It should put the data there, and now you have a project directory that contains your data. If you go on the left side of the GUI and you click a couple times on last modified, then that project should show up with a check mark next to it. So there it is. That's my project, has data in it. I can check and make sure that it really looks like what I want it to be by going down to the bottom of my screen. It says current directory, users, Terwilliger, blah, 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 browse, or a magnifying glass. If I hit the magnifying glass, which I'm going to do, my Zoom is covering that up. Okay, opens up a browser window in that directory. So if you want to work with any files in that directory, they're right there. So we're going to close that. We don't need it now, but we actually will do that a little bit later. Okay, so now we have files that are ready for our tutorial. And I'm going to tell you the next thing we're going to do is next we're going to examine our starting map. So I'm going to copy and paste this into our chat so you can see it. So we're going to open Great. Thank you, Claudia, for those comments. That's perfect. So we're going to open Coot now and just have a look at the map before doing anything. So on the top of the Phenix GUI, there's a button that says Coot. And if you hit that button, Coot should open. If you open Coot the very first time, it takes like 10 seconds. So don't worry if it doesn't come up right away. So now I've got Coot open, and I would like to have a look at the starting map. And we also, I think, have a model that we can look at. So I'm going to go Coot, file, open coordinates, and there's rotavirus.pdb. So I'm going to open that. There's our little piece of rotavirus. It's not the whole thing. And then I'm going to do it again, File, Open Map. And I'm going to select the rotavirus blurred map. And there's my blurred map, and it looks pretty blurred. Yeah, and I see some really great comments in the chat there. So sharpening, as Paul said, doesn't change the resolution of the map intrinsically, though in the process of auto sharpening, we actually do cut the resolution in the high resolution range. So basically, the things that are adjusted during map sharpening in this automatic procedure are the overall fall off of the weights on the Fourier coefficients with resolution, and then a high resolution limit where then it suddenly falls off very fast. Okay, so this map, is fine, but it's pretty low resolution. So let's now automatically sharpen this map, and we'll see that it gets a lot better. And one of the things you're going to learn in this exercise is that just if you look at a map and it looks like this, that doesn't necessarily mean that the map doesn't have any high resolution information in it. It could mean that, but it doesn't prove it. And we're about to see that. So now we're going to run auto sharpening. I'm going to paste this in to the chat window again for you. So here's what we're going to do. We're going to go to back to the Phenix GUI, and we're going to select Cryo-EM, and that'll open up the possibilities, and we'll scroll down a little ways to auto sharpen map. And you can click on it once. Once is all it takes. It may take a couple seconds to open, and then it'll pop up a little window for you. And most of the Phenix GUI entries look a lot like this. There's a front page where you put in a title and files, and then there might be another page that where you might set parameters. So let's always put in a title, and I even wrote in what your title could be here if you want to just cut and paste it so you don't have to type it. So type in something there, and when you're really doing something, type in something there that defines what's different about this run from every other run, because you can look at the titles later and figure out which one was the one that you liked. So now we need a map file, and our map file is going to be rotavirus blurred. So if you hit browse, it should open up in the same directory where we've been working, and we can double click on or select and open rotavirus blurred map. If anything went wrong, this would turn red or tell you it wasn't a map or something like that. We need to tell it what the resolution is, and we can say 2.6. It doesn't make a whole lot of difference in this particular case. This is the resolution that's the nominal resolution of the map, and beyond this resolution is the resolution where it's gonna, the weighting on the Fourier coefficients is gonna be damped way down. It's up to this resolution where we're gonna be adjusting things. If you wanted to use model-based sharpening, you could put in a model file there. The model-based sharpening doesn't use the details of the model. It uses the overall comparison of the model versus resolution to identify what's the optimal sharpening. But we won't do that right now. And we can name the sharpen map file if we want, but we don't need to. So we're just gonna hit run, and it should do our auto sharpening. This won't take very long for this. So it reads in the map, tells us a little bit about it, tells us in particular what's the effective B value of the starting map. So this is how fast the weighting on the map falls off with resolution, and that had a number of 300. So that a B value of 300 is like a map that might be a 6 to 8 angstrom map, which is about what that looked like. So once it's done, it tells us what it did, the method. Here it applied effectively an overall B sharpen of 200. So it went from 300 to 150 for a final B value. High resolution cutoff was 2.6. And it used this adjusted surface area that I mentioned to do the sharpening. If we scroll down to the bottom of this page, there's an open in Coot button. If we're lucky, we can hit that button and it should open this map on top of the existing one. A lot of times these windows have a list of files like here and an open in Coot button. Generally, if you select any of them, the appropriate things will be opened in Coot on top of whatever else is already in Coot. So we can try that. Notice that you can select things. So we're going to open the sharpened map, hit open in Coot, and then our Coot window should show a new map if we're lucky. And mine's a little bit covered up because of zoom here, and I have to find it. Okay, so here's my map. Okay, and I'm gonna hit display manager. I did that too fast. In Coot, select the display manager, and we're going to adjust the properties of the sharpen map so we can see it. So if you hit properties, let's change its color. Should put up a color wheel. Let's make it yellow. No, let's make it red. Sorry, I was going to do everything red. Make it red. Okay. And also let's change, we don't need this time, but it just get a set for other times. Let's set the level, this and at 5 and RMSD. So that's the map contouring is going to be at 5 sigma and change by RMSD. Let's make that 0.3. And then we can hit OK. Those values are convenient ones for adjusting the contour level. So I'm going to move this display a little bit out of the way, and I'm going to turn off the blurred map, and we can see our sharpened map, and it looks pretty nice. So in a way, you might think that's a little bit magical. We started with this, and we just sharpened it. We got that. But just to remind you, that information was always there. It was just dampened down in this map and accentuated in this map. And we just adjusted the relative weighting of different Fourier coefficients to make the map as clear as possible. Now, let me just look at if there's any questions. Are there any questions that didn't get answered yet? Paul, just tell me if I need to answer something.
There was one question about how does local sharpening work that none of us got to yet.
Okay, I'll address that. So what we just did was global sharpening. We adjusted overall the sharpening of the map to optimize the overall view of this map. You can carry out essentially the exact same process in little boxes around the map and then smoothly go from one to the next. And that leads to a locally sharpened map. So you can do that, and that's an option in map sharpening in Phenix. I must tell you that I have never actually seen a map with any local sharpening that actually is better than global sharpening, even though it may appear initially to be better. So it's fine to do it. It won't hurt anything, but in my opinion, it really doesn't help. Which B factor should be mentioned? Yeah, in the output, there's a where's my final B iso obtained. If you want to cite some number for what the final overall Wilson B factor for the map is, you could cite that number. these kind of numbers, as well as resolution, frankly, are not that helpful. People don't have a uniform definition. They don't have a uniform definition of Wilson B factors. So if you use the same program and you do this the same molecule and you compare these numbers, there's a good comparison. Any other comparisons have some merit, they have some utility, but they are not going to give you a really precise estimate of anything. And similarly, particularly the resolution, we're going to talk about that a little bit later. If you use a model for sharpening, you need to consider the symmetry. So you have two choices there. You could supply, if you supply a small piece of a model and use that for model-based sharpening, and you don't do it locally, you do global sharpening just like I did in this example. If you do that, then only the region where you supplied the model is going to be examined. So then in the region where you supplied that model, no matter how small, the optimal sharpening of the map in that region will be calculated based on a comparison to the model, and then that will be applied everywhere. No, you do not need to choose the initial B ISO value. The initial B ISO value is just what was found. And actually the answer that you get depends only in the slightest way upon the initial sharpening of the map. It does depend a tiny amount, but almost doesn't. So you basically don't have to worry so much about that. Let's see, any others that I missed, Paul?
Just look at, well, is there an equivalent tool for auto sharpen for crystallography?
You can actually use auto sharpen on a crystallographic map if you want, but in fact, it's not generally necessary, and it's not generally that useful in crystallography. So in crystallography, we sharpen the maps all the time in crystallography. If you run auto sol or auto build, it automatically sharpens the map based on the resolution, and that works pretty well actually. You can actually, though, run auto sharpen on a crystallographic map, it'll run. Yeah.
There was also a question about how does auto sharpening in Phenix compare to post-processing in Relion, which is sort of a sharpening process as well.
They're related, and in my experience, basically you can take the output from Relion and tune it up a little bit with auto sharpening in Phenix, and that's generally the best way to go. There's actually several different approaches one can use for automatic sharpening. So the one that I described here that we just used basically looks at the map and tries to make a map that looks the best. Another approach that you can use for automatic sharpening is to compare, as a function of resolution, the Fourier coefficients from two half maps being maps where half the data was used, and so the two half maps are somewhat independent, and therefore a comparison of them allows you to identify how accurate the data are as a function of resolution, and then you basically weight the data by how accurate it is. That also works pretty well. In my experience, using the visual approach works a little bit better.
So there's another question here. Would you take a refinement job output? I assume that's the refinement of a model against map, and put that into auto sharpening.
You certainly could do that. If you're doing global sharpening, using a model is a perfectly fine way to do it. And you can use any model you want. And the more accurate the model, the better the sharpening that you get out of it. So yeah, sure, it's fine to refine a model and use that to adjust the sharpening. Notice that if you're doing global sharpening in this way, you're basically adjusting two parameters. So you can't possibly be biasing your map in any serious way. So you don't have to worry about that.
So quick clarification from Valeria. I mean map refinement in Relion. Is the map refinement in Relion different from post-processing, I guess is the question.
I don't know the answer to that question.
Yeah,
Oh, so
so
you're
I
saying
guess
half map sharpening. Should you input original half maps or filtered half maps? Oh, half maps for pretty much everything in that we're going to be talking about. You want the original half maps. Half maps, actually, yeah, half maps, unsharpened, unfiltered. Actually, filtered is okay, but it doesn't make that much difference. But you definitely do not want them to be masked. That's the thing that would be very serious. That would be a big problem. Okay, what map to use for further steps? So generally speaking, what I would say is you're going to come in with 2 half maps, maybe a full map from Reliant or whatever program you just ran. And you're going to auto sharpen your map as a first cut. And if that map is more clear than your starting map, use that map. Once again, at this stage, you haven't really lost or gained anything fundamental in the map, but you could imagine that if you did refinement against that low resolution map, it wouldn't work nearly as well as refinement against the high resolution version. So basically, at this stage, you're going to want to take the map that is the most clear and use it for your next steps for model building or refinement or whatever you're going to do next. This is also going to be true for density modification we're going to do in just 1 second. Is the post-processing and Reliant and auto sharpening the same thing? They're different processes. They both have somewhat of the same goal. Is the BISO an absolute scale? That's an absolute scale. So BISO is an exponential, is the term in the exponential that says how fast things fall off. So so that's an absolute number. Yeah, that's in angstroms squared. Okay, so let's move on for a second to
just a question about kurtosis value.
So kurtosis is another method of examining whether a map looks like a nice map. And typically, the high kurtosis values are also the place where the map adjusted surface area is high. It's another method for choosing the best, and you can actually use that if you want. I wouldn't say there's any number for kurtosis that's good and bad. It's generally for a particular map, higher values are better than lower values. Okay, so let's one more question here. Should I use original half maps? Yeah, so we're going to do resolve Cryo-EM now. And I think it's asking, should we do sharpening first and then density modification second? Yeah. So they're sort of separate, independent. I'd run sharpening just like we did. And I would also run density modification. And then whichever one gives you a better looking map, I'll take that one. Density modification contains sharpening in it. So you don't normally do sharpening after density modification. Okay, so let's do this. Wouldn't it be sharpening twice if you perform post-processing as well as auto sharpening? Yes, absolutely is doing it twice. It's okay. There's some things that you wouldn't want to do twice. So density modification, you wouldn't want to do that twice. Auto sharpening doesn't change the Fourier coefficients except to weight them versus resolution. So you haven't really done anything fundamental to the map. So you could auto sharpen and then you could density modify, that's okay. Once you density modify, you fundamentally change the map. You don't really want to modify that map again after that, usually. Okay, let's close our COOT window. And now we are going to do some density modification. Let's make sure, oh, that wasn't the one I wanted. Cut. There we go. Okay, so now we are going to do density modification, and hopefully this will answer some of the other questions. And let's set up our tutorial. So let me paste that in for you again, as usual. Oh, there was one more question on sharpening. How does local sharpening differ from other programs like local deblur? It's actually, it's related, once again, same goal with slightly different approach to actually do it. And many of the other methods that are local methods use a model locally to compare the map and model, and in a way very similar to the way auto sharpen does that. Auto sharpen is the only one that uses this, let's look at the map and look at its connectivity and look at its surface area to try to figure it out. So the other ones are different approaches, once again, same overall goal. Okay, so let's do some density modification now. So we want to do a new project, set up tutorial data. So same as before, new project, set up tutorial data, and select a data set, scroll down, and this time we're going to do human apoferritin density modification. So it's the second one under Cryo-EM. And you can put that wherever you want with your browse. I'm going to put mine in demo, open and OK. And then you should have your data. If we click on last modified a couple of times, we should be able to see it. With a check mark, there it is, apoferritin density modification. And if we looked at the bottom, it tells us that's the directory we're working in. Great, we're all set. So once again, in the Cryo-EM, oh, why is density modification needed after auto sharpening? So actually, I'm suggesting you do them separately, but you could do it after auto sharpening. So let's have a look at, let me try to answer that map by looking at a map in 1 second. So we're gonna go Cryo-EM. So we're gonna, let's see. Oh, I forgot one thing. So we wanted to examine the starting map. So let's do that. At the top of the window, we're gonna hit Coot. And we are going to go to File, Open Coordinates. So this comes with a human apoferritin that's refined against this map already. And that's called apoferritin chain A rsr.pdb. Let's just open that. We're going to use this as a reference, and we're going to use it to cut out the map a little bit later too. So, okay, and we should get a picture of one chain of apoferritin. And then we're going to open our starting map, which is, so open map. And that, if we filter, we'll find it. Filter EMD 20026 auto sharpen A.ccp4. So this is the deposited 1.8 angstrom apoferritin map from this set of data that's been cut out to match this chain. And I'm gonna hit OK. And this will take a second to load because it's a little bit big. And now we're gonna do that same trick that I mentioned before, where we are going to go to Display Manager, Properties of the map, and we're going to set the level of the map to 5 sigma, that's RMSD, and change by, let's say, 0.3. And we hit OK, and that will allow us to scroll on this map, and it won't take too long to scroll down and be able to see things. So if you don't do this, then when you scroll on your mouse, it can kind of run away from you, and it may take a long time before you can see anything or do anything on the screen. Okay, so let's look at a few places in this map. In particular, we can use the draw go to atom tool in Qt. It'll put up a window that allows us to define where to go. And let's just type in residue 81 just so we can go to the same place. So 81, and we can close this. So residue 81 happens to be a place where in the human apoferritin structure, there's 2 conformations, in fact. And I'm going to adjust the contour on this starting map so we can see which one is the right one. So we see it's the one on the left. But the map is not all that nice there. And also notice that the map has a lot of noise everywhere. This map is actually, so this was auto sharpened. And I would say this map is actually, it's not optimally auto sharpened in this particular case. It's noisier, it's over sharpened. The high resolution information is accentuated more than it should. The density map does not cover the model just because Qt shows a circle, a sphere. So if I selected a different part of the model, now the map is going to show the other part. Yes, Claudia, it was a 5 sigma and step of 0.3. That works well. Yeah, so I guess somebody else answered that. Thanks, Dorothy. Okay, so this map is not perfect. It's a very nice map, but it's not perfect. So let's density modify the map. Let's talk about what we're doing in that, and then let's come back and see what happens. So now let's go back to our Phenix window, and we're going to run density modification. So we're going to, let me paste it in, how to do it. Okay. I didn't mean to click refinement. So we're going to go to Cryo-EM and then scroll down to resolve Cryo-EM for density modification. And move that a little to the side so I can see my window. And once again, let's put in a title. And this is going to be apoferritin tutorial, or whatever you want to type there, doesn't matter. And for density modification, we're going to need 2 half maps. So once again, each of these half maps was generated using half of the data. These 2 half maps are superimposed upon each other, so they have exactly the same orientation of the molecule. And hopefully they're relatively independent errors in these 2 half maps. So if we browse, we should be able to see a file called emd2026 halfmap1 box.ccp4. So this map has been boxed already. I cut it out of the full map to just to remove the outside of the map. So it just makes it a little smaller. Normally, you can supply the full size map, and Resolve Cryo-EM will box it for you. In this case, to make it smaller so it can package it easier, more easily, we already boxed it in advance. Okay, so we can select that, and that goes in for half map 1. And then we can do the same thing for half map 2. Then we need to tell it what resolution for the nominal resolution of the map and the resolution that we're going to use for density modification. So we're going to use 2.2 as the nominal overall resolution of this map. And that would be the number that you got from Relion or whatever program that you ran. And then a resolution for density modification, that's normally set for you automatically, but just so we're all on the same page, I'm going to type in 1.8 so we all use the same number. We need to, I need to mention again, so we want to input unmasked half maps. So we don't want to supply a map that's been masked around the molecule, because actually we're going to need the noise to give us the answer here. And I'll talk about that in a second. Okay, then we need to tell it something about how big the molecule is, and we can give it a sequence file that contains all the chains that will tell it how big it is. So I hit browse, and seek.dat has that information. This sequence file actually has all the chains, and later on we're going to have to make one that has only one chain for another purpose. We could also have supplied one chain and said there were 24 copies. That would work fine too. Important uncheck in this case, the box before analysis, because we already boxed this map in advance, so we don't need it to be done automatically. So if you want something to be false, you uncheck it so it's blank. Let's set let's see, we did that. Quick run, yep. Number of processors, let's set that up to 4. And then 2 more things. Let's density modify unsharpened maps. And so the minus means do default. Check means do it. Blank means don't do it. So we're going to do that. Check. And what that basically means is in the first step of density modification, it does automatic map sharpening. And we're not going to use the result of that. And it just happens in this case, it works better without it. The default is to do that. And then another one is final scale with FSC ref. Basically, that adjusts the final resolution dependence to match the expected fall off of a normal protein. And it just takes a little extra time, so we're going to skip that in this particular case. So we'll turn that off. Also, we're going to, just to speed things up a little bit, we're going to do fewer resolution bins. We'll do 20 instead of 100. And that's everything we're going to do right now. If you had a model, you can put it in, does a different process, and ask me later to tell you how that works. So everything else should be default, and we're all set. And then we can hit run and run now. And if we typed anything wrong, it should pop up a little window and say you did something wrong. Otherwise, it just should start running, and then we're fine. Okay, so if it gets past a little bit after this, then it's read the maps. Okay, everything's cool. All right, let's see. Is there any questions I need to answer here, Paul?
There's a question about, do we have to choose a box before analysis option?
Yeah, so normally, yes. So I'm gonna click configure here. You don't need to do this, but if you click configure, you could set up a new window and run it again, whatever. So I can just see what I did, and I can tell you. So this box before analysis, normally you have that checked. So yes, normally you want it to box before analysis. And the reason to do this is a little bit non-obvious and not perfect. Basically, if your map is really huge and the molecule is very small in it, most of your map is basically 0. And the farther away from your molecule, the less noise there is. And the fact that there's almost 0 noise way towards the edges is going to confuse resolve Cryo-EM. So the purpose of the boxing is to create a map where your molecule occupies maybe 25% of the volume, and the whole thing is then like 4 times bigger than your molecule, and most of the non-molecule area has kind of a uniform noise level. So that's because it's not perfect. It would be, the perfect thing would be to be able to take that all into consideration, that it falls off with distance and all that. And we don't have that, so therefore boxing is a very convenient way to make it relatively uniform outside the molecule.
So, but that automated option is suggested rather than doing it manually somehow before.
Oh yeah, so I would try it with the automatic first. If you don't get a good result, like the density modification doesn't seem to work well or something, then you might want to box it yourself. And the way you would do that would be you'd want to create the situation I just described. Your molecule, including things like lipid or whatever, is about a quarter of the total volume. And if it didn't do that automatically, if it didn't generate something like that automatically, you can box it. Another reason you might want to box it yourself is that your map has some things in it that Resolve Cryo-EM doesn't expect, like big noise peak somewhere that you want to just box out. Or maybe your molecule, like I was describing a second ago, maybe it has lipid in it and you want to try it kind of keeping all that lipid and treating it as if it were solvent, or making a bigger box that treats the lipid as if it's part of the molecule and solvent separately. So you might want to basically adjust the size of the box and just see which ones give the best result. And once again, for density modification, usually you just run it like we're going to do here, you get a result. And either that map looks more clear or less clear than you had before and you're happy or not. That's usually what you're going to do. But there are a lot of things you can change. And if you have the time and energy to look at the maps that you get after different options, it's worth doing that, and you may be able to improve it. You can also run multiple, and we can just mention a couple of those things here. So I mentioned the density modifying unsharpened maps and final scaling to make the resolution fall off look like a typical map. You can do that. Other things that are optional are you can do more than one cycle, in which case it takes the result of the first density modified map and then density modifies that, and that can sometimes improve things. Real space weighting is kind of a local sharpening approach. Basically, it takes the assumption that maybe some places in the map, the density modified map is better than the original. And in other places in the map, the original is better than the density modified. This uses a comparison of the density modified half maps to identify where the good parts are, and a comparison of the original half maps to identify where the good parts are there. And then it does different weighting in the two, depending on position. You can do a similar concept where you're weighting in reciprocal space, where you're weighting some Fourier coefficients higher than others. And that's another option. Both those two take a lot longer, in which case you may not want to do them. Yeah, more questions?
Yeah, a couple more. Maybe this first one's a quick one. What would you recommend for a huge map, like an icosahedral virus?
Yeah, it's a really great question because it's a really important point. You can't density modify a piece of the map. You have to density modify the whole thing. So yes, you can cut out the molecule out of a huge box, but no, you cannot cut one chain out of a molecule. It doesn't work. I mean, I've hoped that it would work. It theoretically shouldn't work, and in fact, it doesn't work. So don't bother trying that one. If you have a huge icosahedral structure, you throw the whole thing in there and you density modify with the whole thing.
But after doing that, you could then reduce down to an asymmetric unit to do later steps.
Exactly. Do you need to add a sequence file if you have a model? Yeah, actually, those are used separately. So you need to tell it how big the molecule is with molecular mass or sequence file or solvent content. And then separately, you may or may not add a model. If you add a model, let me tell you what happens if you add the model. In the first cycle, when you add the model, the first thing that happens is you do density modification in exactly the usual way, ignoring the model completely. And then in a second stage, that model, if you supply just one model, that model gets randomized using Pavel's tools, actually, so that you make 8 different copies by default for each half map that are as different as they can be, that agree still with the map. So you generate some diversity both by half map and by just multiple copies for each one. So for each half map, you generate a bunch of models that are now somewhat diverse. And then you use those, and then they're each refined against the separate half maps. And then in the density modification process, the density that's calculated from the average of a group of models for a particular half map is used as part of the information about what is good. And we're going to talk about that now in just for a couple minutes. As soon as I'm done saying this, I'll tell you how this works. So basically, we're going to use some model-based information, and we're going to use the variation between densities corresponding to these different models as an estimate of uncertainty in the model-based map. We're going to combine that with the map, the information from just the map that's already there. And that combined information is going to give us a better map. So we're not going to do that one today. It takes a little bit longer, but it can give you a bit more information. There is potential for model bias, definitely. In practice, we don't see model bias, but you have to be aware that it could happen. Okay, so let's talk just a little bit about how density modification works. So let's go back to our presentation, and let's open that one up. Okay, so. Okay, so let's see, there we go. Okay, so density modification is totally standard for X-ray maps. Everybody does it all the time, and they've been doing it for 30 years, and everybody knows it works. So it was a little bit of a question whether you could do this with Cryo-EM map. And let me just briefly say why you can. So here's a picture of an X-ray map of GROL. Here's the same structure, but it's a Cryo-EM map. It will pop up eventually here. There we go. And you may have barely noticed that they're different. So the maps for Cryo-EM and X-ray, if you're able to superimpose them, they look really, really similar. So maybe the properties would be similar. And actually, both of them come as Fourier transforms. So a Cryo-EM map, it's really taking a long time to come up. There we go. The Fourier transform of one image, so the Fourier transform of one of these pictures is a section through the Fourier transform of the structure. You don't have to really understand all of that, but the key is that we're dealing with Fourier transforms for a Cryo-EM map. And in X-ray, it's actually very similar. One picture diffraction pattern is more or less a section through the Fourier transform of the structure. And whereas in the X-ray, you only get the amplitudes. And so to get an X-ray map, you combine the sections to make a 3D picture, and you get the phases some other way, and you do an inverse Fourier transform, you get a picture. In Cryo-EM, you combine the Fourier transforms of all the sections to make a 3D Fourier transform image. You do inverse Fourier transform, and you get a picture. So they're very similar and have a lot of the same properties. So how does density modification work? The key thing here is that you have to have an idea about what to expect about a map. And the key thing here is that if you know something about what a map ought to look like, you can use expectations about one part of the map to improve another part of the map. And that's the crucial thing. You're going to improve a different part of the map. So maybe our original map looks like the one on the left, and that actually is this map we're looking at. But we know that the map should be flat. But in fact, in the solvent region, there's noise. So we know that that's not right. Another thing that's actually maybe more powerful is that we have a good idea about the distribution of density values, histograms of density values, and what they should look like in a protein molecule. And basically, within a protein molecule, most of the values are very low, like all these values between the atoms are very low. And then suddenly it gets in a very short distance, goes up to a very high value. So basically there's a lot of very high value, some very high values, and many, many relatively low values. In a noisy map, it gradually goes between one and the other. And on the right, in a good map, it goes sharply from one to the other. And also in a good map, the solvent is relatively flat. So we can know by looking that the map on the left is not as good as the map on the right, just from those general characteristics. You could also know the map on the left is not as good as the map on the right because that tyrosine doesn't look as good as the one on the right. So we can know that this one is better in several different ways. So how do we actually do this? So these maps are calculated as a sum of Fourier terms. And the property of calculating a map this way is that every Fourier term, every coefficient, affects all the points in the map. So if we changed one term and just took out one term that represents part of this Gaussian, it would make a ripple in this case, the entire map. And so a way of looking at this is that an error, if we make a mistake in one Fourier term, it leads to correlated errors everywhere in the map. In particular, it makes, in this simple Gaussian picture, makes the Gaussian atom look bad, but it also introduces ripples elsewhere. So the trick is if we fixed a Fourier term based on one of the part of the map, if we looked over here and said, I know the solvent should be flat, let me fix this Fourier term, that can fix the map in another part of the map. So the way we actually do this is one term at a time. We find the value that yields the most plausible map, leaving all the other terms fixed. And then those Fourier terms collectively, taken all together, improve the entire map and yield what we call a map phasing map. So here's the procedure that's actually done in Resolve Cryo-EM. Oh, let me see. Is there questions I need to answer before I go on to here?
There is one question. Well, there was a couple of questions. One question, though, the latest one is a question about if the half maps have filtered, would that be a problem for the density modification?
Yeah, so it depends on exactly what you do in this filtering of half maps. So if the half maps are filtered in any way that masks out the solvent relative to the protein, that would definitely negatively affect density modification. If the half maps are filtered sort of with default rely-on characteristics, it works pretty okay. But in our experience, the very best maps for density modification are the ones that are the least filtered. And if you can tell that because the solvent looks noisiest. Okay, so here's our procedure. We're going to start with 2 half maps. And then we're going to create 1 full map by sharpening and averaging them. So basically doing auto sharpening. And then we're going to identify the regions where it's macromolecule and where it's solvent. And this is where the solvent content or sequence or macromolecule volume or mass comes into play. That helps decide basically how big that region ought to be. It doesn't have to be that accurate. This is done automatically, and whatever you put in doesn't define exactly what the final solvent content and masking is going to be. And then using so we're going to define a mask essentially that says this is where the molecule is, this is where the solvent is. And then we're going to look in this full map, which is better than either half map. We can use the full map to identify target histograms for the macromolecule and solvent. So basically we're going to say, I think the full map in the region of the macromolecule has histograms that are more what I would like to see for the histograms for these half maps, and similarly for the solvent. So the histograms for the solvent will be relatively flat for the full map. So now we have target histograms. Then we're going to go into Fourier space. We'll calculate Fourier terms for each of the two first half maps. And we're going to, for each half map, once again, we're going to use these target histograms to identify how to change the Fourier coefficients in those original maps, just the way we talked about in the previous slide, to generate map phasing estimates of each half map. So basically, improved half maps generated based on expectations from the right-hand side, and original half maps based on data from the left-hand side. And then we're going to calculate the weighted average of those two maps to generate a new half map, and then we're going to average those to generate one full density modified map. Let's see, were there any more questions on that before we?
There is a question about, do you have an example of the density distribution histogram?
Yes. Let me pull out of this tutorial and I think we can find one real quick.
And there's a question about how can we obtain these distributions, but I guess you'll explain that they're pretty uniform, they're pretty constant. They're not case specific.
These density distributions, actually there's, so in this, the way I'm describing it to you, we're generating these density distributions on the fly for a specific case. You can also use density distributions that are typical density distributions. In fact, turns out the ones from X-ray work pretty well for the Cryo-EM, and that's often what's done here. Okay, so I'm going to open a little presentation here that does have these histograms in it, I hope. Okay. So here's a picture. This is from X-ray, but it's actually just the same thing. So here's your nice density map on the left, and the right-hand side shows a histogram of density values in that map, where there are, most of the values are kind of around 0, and there's a few more at high values, and there's essentially none at low values. So, and then here are the next slide shows real ones. So in this real example, a good map, which is the dotted lines, shows, once again, most points are around 0. And then there's a few points that are extra high. And that corresponds to the points that are on top of atoms. And a random map has a distribution of density values that's almost a perfect Gaussian, the solid line. Okay, let's close that one. And I think we're done with this one too now. Okay, so now let's go back to our Phenix window, where hopefully everybody's density modification run is finished. Oh, so we're already a little bit late here. Yeah, well, I'm gonna go over a little bit on this one, and then we'll go a little bit shorter on the next one. I wanna just tell you a little bit about what results we see. So when we ran, there was a log file that just kind of described everything that happened along the way. And in particular, I won't go through in detail, but I'll tell you that it talks about, just right in that log file, it talks about the error model, about how these maps are combined and how all that works. And then it tells you about what the values are for all these error estimates as a function of resolution. And S, for example, is uncorrelated error in the individual half maps. A is correlated error, and so forth. So all those numbers are right there for you to look at, and they're printed out for you. And if we go back into the main tab here, it says FSC half maps. This is your Fourier shell correlation. That is correlation of Fourier coefficients as a function of resolution of the original half maps. And here, these fall off to a value of 0.143 at about 1.8 or 2 angstroms, something like that. And this number is special just because if everything was totally random and nice, then if you had two half maps that have in a particular resolution shell have a correlation of 0.143, the correlation of their average to the true answer would be about 0.5. That's where this 143 comes from. So this is the FSC map Fourier shell correlation of half maps. The next graph is the FSC ref. That's the estimated Fourier shell correlation to the true answer of original and density modified. So the FSC ref original in brown, it goes to 0.5 at that same resolution that we were looking at before. So this is the estimate of how good the map really is based on the Fourier shell correlation between half maps. The blue is the same thing for the density modified map, where now it's not exactly based on the two density modified half maps. It includes the full error model that I described a second ago. So you can't just do a Fourier shell correlation between your density modified half maps and get this exact number. This number is a better one, but as I described before, resolution estimates are really very approximate in Cryo-EM. Okay, but in any case, it looks like it's a little bit better. And our results tab says that it seems like the resolution improved by 0.04 angstroms, just a little bit. For very high resolution maps, that's not abnormal. If you have a low resolution map and you're lucky, this number can be much bigger in some cases. It can be as much an angstrom better. More typical would be maybe half or a third of an angstrom. Okay, so now we're ready to look at this new map compared to the original, but I want to do one thing. We're going to cut out, we're going to box this map so we don't have to look at the whole thing. So this map is pretty big, and in Coot, it's a little bit hard to look at. So we're going to make a box around this map. So let's do that. Need to get everything out of the way. And so we're going to cut out our map around a supplied model. So let me paste that into our window. So we can close that density modification window if you want. So in the Cryo-EM tab, we're going to select map box. It's down a little ways near the bottom. So if we select, let's see, how did you determine density modification resolution? So that resolution was the resolution calculated based on the error model that I described in the log file for the resolution at which the estimated resolution where the density modified map has a 50% correlation to the true map. So it's our best estimate of the resolution where the true map and the density modified map have a 50% correlation. Okay, so map box. And so what we're going to do here is we're going to cut out our density modified map in the region of the model, of that same model we supplied. So our job title is, we're going to box this map. And our map file is in a directory called resolve Cryo-EM 1. So I can double click on that, open up my map file. And this time, yeah, we do want a model. We're going to browse. And it leaves me in the directory where the density modification was. I need to go up a directory to where we were working. And I can look down there, and there's my apoferritin chain A rsr.pdb. So we're going to box around this model. So this map box doesn't do anything to the map. It just cuts it out. We're going to do, we're going to write this map. Let's name the output file. And the prefix here means this is everything except the .ccp4. So let's call it denmod map box. So it's boxed, something like that. And we're going to mask it using the model. So the model will define how big the box is. We're going to do one more step. We're going to mask around the atoms. So this is going to cut out everything that's more than 3 angstroms away from an atom in this model. This is going to be, we're going to use this for model building in a second. It just makes everything a little bit easier to see and quicker to work. There's many other options. You could select where the density is. You could extract the unique part of the map. We're not going to do any of that. We do need to do one extra little thing here. So if you're doing this map boxing, be sure you do this one step. If you don't, it'll just give you an error, and we'll need to do it. It turns out this model has a information about the crystal symmetry in the model that's not right. So we need to tell Mapbox to ignore it. So we're going to go all parameters at the bottom of Mapbox, search parameters, and we're going to type symmetry into search. It's going to find all the parameters that have the word symmetry in them. If you hit OK, there's only one. And it says ignore symmetry conflicts. So let's check it. Oops, check it. And OK. So now if the model has the wrong symmetry, it'll just ignore it. We don't have to worry about it. Now we're ready. We just hit, let me check I did everything I told you to do. Mask atoms, search, OK, run. OK, just hit run. This takes just a second, and it will box the map for you. OK.
Tom, there was one additional question for density modification.
Yes.
So you choose 2 resolution limits. I think one was 2.2 and then a higher one, 1.8. How would you decide about the 1.8, the higher resolution limit?
Oh, that's a great question. Normally, just leave it blank, and then you don't have to decide. And what'll happen if you do that is, if you do everything kind of by default, it'll use a slightly higher resolution for density modification than the nominal resolution. And of course, it's got to do that because how else can you improve it if you don't even try? But it's not obvious exactly what that number ought to be. And so the default is to use the average best value from a bunch of test cases. So that's what it does for you if you don't tell it anything. If that doesn't work the best, you can change that a little bit less, a little bit more, and you will get a different answer. And that's just a matter of trying it. Also, one of the other options in density modification was that I glossed over, was you can actually have it make many tries at in each cycle of density modification. And it can choose which one it thinks is best based on how well the density modification procedure goes. And one of the options there is to vary that resolution. So you can, another way to go about this is you let it try everything and vary the resolution and pick whichever one works best. So you can do that automatically as well. You'll do better if you do it yourself, but it's quicker if you let it do it. So that's up to you. Okay, so I'm going to hit open in Coot here. I don't know if that worked. There we go, open in Coot. Should open that map. Yeah, it's thinking. There we go. So yeah, I opened that in Coot too many times. I'm going to get rid of that next one that I made. And my Zoom window is overlapping my coot. Okay, so I'm going to go to Display Manager and see if it put up the things I was interested in here. So denmod map box.ccp4, that's the map we just created. And let's adjust its properties so we can see it a little more easily. So I'm going to hit Properties for that map. And let me change the color to make it red so it'll be different. And let me change that contour to 5 sigma RMSD and 0.3 for how much to change by, and hit OK. And now I should be able to scroll easily with this map. Okay. And so let's come back to the same place we were looking before, and we can compare the maps that we've got. All right. So you can see I just adjusted that to optimally look at that phenylalanine. So our original map was not that great in this region, and it was noisy generally. I told you it's a little over sharpened, and you can get a map that looks a little bit better, but there's no way that I can figure out that you can take that starting map and auto sharpen it and make it look nearly as nice as our density modified version. So it's really cleaned up both by reducing the solvent noise, which of course it does because it's flattening it, but also improves the details of our molecule. And so this residue is pretty good. Another one that is improved quite a bit is residue 13 here, another side chain. And looks pretty nice here. The original was pretty noisy. And once again, you can adjust the sharpening of this one so that you can see a little bit better, but it's still nowhere near as good as the density modified version. So this is a very nice map, of course, and there's many places in the map that both original and density modified are really great. So here can we look at, I'm going to do that. So a lot of places you can see are good in the original, but the clarity is generally speaking a little bit better in density modified, and some places are much better. And that's typical for a high resolution map. You should be able to see some things that are much better. A lot of it might look quite similar in the two cases. Also, you can make yourself think that something's better sometimes when it really isn't. And just think back to that rotavirus map that we looked at. You might have said that first map is terrible and the auto sharpen map is great. But in fact, those maps are really fundamentally the same. They're just looking at them in a different way. So whenever you do density modification or map changes of any kind, it's good to vary the sharpening of the different maps to make sure that things are actually really different and not just different because of the way you're sharpening them. There are actually tools in the auto sharpening Phenix tool that allow you to match the sharpening of two maps, for example. So that the resolution dependence of two maps becomes exactly the same, and then you can compare maps using that. So if you're trying to do something systematically and asking yourself whether something is really matched or not in an optimal way, that's probably the best way that I know to do that. Okay, any other questions that I missed here, Paul? Membrane protein, yeah.
Yeah, question about detergent belt. Would you also supply a model from Mapbox? I'm not sure I quite understand that question.
Yeah, so so the reason we did this map box just now was just for convenience, so that we could have a small map to work with in the next step. And I boxed it around the model so that I didn't have to worry about any extra density, and so our model building is going to be easier than it would otherwise be. That's the only reason we did it just now. Now, in real case, you might box the map to work with a part of it. Normally, you wouldn't have a great model to work with because you're just building it. And if you had a membrane protein that had a detergent belt, you can adjust. You might want to cut out the map around the model, sure, and you might want to adjust the there's a buffer around the model where the map is cut out. So basically you cut out a box that's a rectangular box that's by default 5 angstroms bigger than the model. You can change that to 10 or 20 to make sure that you include your detergent belt. You can also define the exact size, shape of the box, not shape. You can just find the exact boundaries of the box if you wish to do that in Mapbox. So if you had a memory protein that doesn't get cut out automatically in the right way, you might want to do that, yes.
And there was a question about what are the possible reasons for density modification not improving resolution in a noisy map?
Yeah, so basically if any of the assumptions of density modification are greatly violated, then it might not work. So, and what are the key assumptions about density modification? One is the 2 half maps are more or less independent. 2, the molecular region can be differentiated from the solvent region. The noise in the solvent region comes from, so this is a key fundamental one. The noise in the solvent region comes from errors in the Fourier coefficients that also affect the noise in the protein region. That is a fundamental assumption that the errors in the solvent region are correlated through the Fourier coefficients with the errors in the protein region. If for some reason that is not true, then it will not work at all. A reason that could be not true is if the solvent region was flattened separately from the protein. Let's suppose you had your perfect maps, everything's great, and you just kind of zeroed out the solvent region and you left the protein exactly the way it was. Now the solvent and protein are totally uncorrelated with each other. You have no information about the protein from the solvent. You just lost everything. And to a lesser extent, if you apply masking procedures, you may do that to some extent and therefore lessen the applicability of density modification. Also, if there's something fundamentally different than the map, than assumed about the map. So, and in fact, the detergent belt is such a case. So the assumption as it is in our density modification is there's a protein or nucleic acid, whatever, region that's well-defined. And then there's a solvent region that's basically flat. So we can identify, we can break the two, separate the two and say histograms for solvent look like this, histograms for protein look like that. What if there's a detergent belt that's kind of in between? So that violates the assumption that they're separate and different. So then you have to treat that one either as it's like protein or it's like solvent. So that one necessarily is going to work less well than it would otherwise. Those are the big reasons.
Okay, so another question is, can iterative model building and density modification of original maps lead to further improvements?
Yes. So we're going to do density model building in a second, or in a little more than a second. And yes, that can be used. Those models can then be iterated to improve the process. The overall improvement is not dramatic. And now maybe someday when this is all done perfectly, maybe it will be dramatic. But if you're from X-ray crystallography, you'll know that in X-ray crystallography, it is very dramatic. You can start off with a really bad map. You build a little piece of model, it gets things a little bit better. You iterate that process 20 times, and then suddenly you got the whole thing. Okay, in Cryo-EM, we have not achieved that. So you can get a small improvement by iterating the process, but it's not dramatic. So let's say maybe you built 60% in one shot, and maybe you build 65% after you do it a couple of times. That's the kind of improvement you're talking about.
Yeah. So what happens in regions in which atoms are wrongly assigned? Does it affect the density modification outcome in that region?
Yeah, it certainly would. I wouldn't call it atoms wrongly assigned in the way we're doing it here. So we're not, in this case, we're not identifying atoms in any particular place. We're just saying this part of the volume is macromolecule, this part is solvent. But if that's wrongly assigned, then the pressure for what it ought to look like is going to be wrong, and therefore it will affect the outcome, yes. So in particular, it is possible that side chains on a surface that are not that well ordered could get flattened a little bit. This happens in protein crystallography. We try to make a pretty big mask so that that doesn't happen too much, but that's a potential problem. So yes, and similarly for the lipid belt, same problem.
Yeah, so last question before we take a quick break. Is there a possibility to input histograms for lipids detergent?
Yeah, so that's on the that's on the list, but that's not there.
Okay, so that's a possibility.
Yeah, no, in principle,
okay, so,
absolutely.
yeah. So yeah, one last question, then we'll have a break, because we do have to get to a break. This is great. It's based on the assumption that we already have a map.
Yes.
What if we're dealing with unknown structure and a homologous model? Well, this is based on having maps. We have to have maps to do this.
Yeah, we can't deal with that situation. Yeah.
Right. Would you deposit a density modified map? Yes, that's a longer discussion, but we would advocate people deposit their original map that came out of the reconstruction, deposit the map that you used to interpret to build the model, etc., and half maps. Those are I think the minimal things that eventually the community will be required to deposit. It gets more complicated if you have focus reconstructions and stuff like that, but for sort of a straightforward case, those 4 things are actually, I think, going to become mandatory.
Yeah, that definitely. And Andre, on solvent that's inside the protein, density modification should be fine for that. It will treat that solvent as if it's protein, that is, as if it's ordered, and not try to flatten it or anything. And so solvent that's, suppose you have a very high resolution map and you're trying to see some solvent molecules that are inside the protein, it should be no problem. I mean, it should be fine to try to look at it with density modified map.